Day 2, oh no, part 2, day 5. All right, so applications of probability. How can I pull it all together? So probability has uses far beyond its origins in games of chance. Often probabilities are based on survey data or data taken from a sample population. Today you will learn a new probability rule and a new way to determine independence. And at the end of the lesson, you will summarize the probability rules that you know. So, in our recent survey of college freshmen, 35% of students check the box next to exercise regularly, 33 checks the box next to eat 5 servings of fruit and vegetables, and 57 check next to neither. So let's make a two-way table to represent this information, including rows and columns. So again, I would love it if you guys would pause the video and go ahead and set this thing up and try to answer the questions that go with it. I'll pause and set it up myself. Go with eat, exercise regularly. So exercise regularly. It's either going to be yes or no. And then it's eat fruits and vegetables. We'll just say eat healthy. Yes and no. So it says 35% of the students check next to exercise regularly. It doesn't say whether or not they eat healthy, though. 33 said that they eat healthy, but it doesn't say whether or not they exercise, so that's got to be a total. 57 said neither, so that's going to go in the middle. They neither eat healthy nor exercise regularly. And then I think this one, sometimes people forget there's 100% of anything, right? So we're asking 100% of people. So this would have to be 67%. This would have to be 65%. This would be 8%, 25%, and 10%. And as always, we add sideways and we add up and down and confirm that it does equal 100%, which it does. So what's the probability that a freshman in this study exercises regularly and eats 5 servings of fruits and vegetables? Right there, 25%. Does both. It's an and question. Has to eat healthy and exercise. All right, so what's the probability that a freshman exercises regularly or eats 5 servings? Well, now we're going to add all these up, right? 25, 33, 43%. The other way to look at it would be to say 33 plus 35 is 68 minus the 25 that said both, and neither of them we get 43%. And it says, do you think that freshmen who eat 5 servings of fruit and vegetables per day are more likely to exercise? Yeah, I would say they are more likely to exercise, but nobody cares. So what we think, we have to actually use math to solve. So let's go ahead and use math to solve and say, hey, everybody, do you eat healthy? And everybody responds 33% yes, I eat healthy. Now we're going to say, hey, those of you people who exercise, do you eat healthy? And we'll compare the numbers. So only the people who exercise, do you eat healthy? And we'd say it's 25 out of 35, which is 71%. So yeah, these numbers are different, so we would say we definitely have an association. So yes, an association. People who exercise are more likely to eat healthy. And that makes a lot of sense, right? We would expect to see something like that. Let me pause and set up the rest. Oh, keep going, I should say. And remember double spin in the game at the fair from chapter 3. The player gets to spin a spinner twice, but only wins if the same amount comes up both times. The $100 sector is 1/8. So Nick is currently playing the game. So draw what this should look like. So let's go ahead and try and make this quick. So there's several different outcomes here, right? So want to make sure that we have all of the potential outcomes. So let's see what can happen here. This is spin number 1. You could get a 100, a 10, a 5, or a 1. And spin number 2, you could get a 100, a 10, a 5, or a 1. This is a 1 in 8 chance of happening. A 10 appears to be a 2 of 8. And again, my preference is a common denominator. So instead of calling it 1 out of 4, I'm going to call it 2 out of 8. I just find it easier to do that. Again, if you want to call it 1 out of 4, feel free. And then here, that's obviously going to be 3 out of 8, right? Because 1 plus 3 is 4, and that's obviously a half. Now, when I figured out the odds, think about this. If I get a 10 and then 100, this is a loss. Or if I get a 5 and then a 10, that's a loss. Who cares? I only care about the winners, personally. So if you want to figure out this whole thing, feel free. I don't. I have a 1 in 64 chance of winning $100. I have a 4 in 64 chance of winning $10. I have a 4 in 64 chance of winning $5. And I have a 9 in 64 chance of winning $1. So it says, what's the probability that Nick wins? Well, there's 1, 5, 9, 18. There's an 18 in 64 chance that Nick is going to win. It says, when Nick comes home from the fair, he tells Zach that he won. Knowing that Zach won, what are the chances that he won $100? Well, there's only 1 out of 1, 5, 9, 18. So there's a 1 in 18 chance. Now, first of all, there's a 1 in 64 chance of winning $100. I understand that. But we already know that the guy won, so we don't have to factor in any of these losses. He already said, hey, I won. So he knows one of these boxes happened, and there's only 18 ways those boxes can happen, and one of those 18 ways is winning $100. It says a mathematical way to express this conditional probability is by getting the probability of A and B, which is 1/18th, and dividing it by the probability of B, which is 18 over 64. So, what I'm going to do here is, remember, we never divide, we always multiply by reciprocals. I'm screwing something up. Give me a second. Let me look into this. So the problem I have is right here. First, I want the probability of A and B, and that is my mistake. It's 1 out of 64, right? There's a probability of getting these two things to happen as 1 out of 64. And then the probability of winning it all is 18 out of 64. So now I will divide these. But again, we never divide fractions. We always multiply reciprocals. And there you can see I have a 1 in 18 chance of winning $100. I'm not a big fan of that multiplication rule. As you can see, I screwed it up right here. I prefer just to use the logic that we've been using. Hey, there's 18 ways of winning. One of those is the $100. But if you want the multiplication rule, feel free to use it. As a matter of fact, my brain sort of turns to pudding when I see stuff like written like this. I can reason through it a lot better than I can sort of make sense of this. By the way, I'm not very good at probability and statistics, so that's probably one of the reasons why, as my brain has trouble sort of wrapping itself around this. Stop is having a sale on bats and balls with a limit of 1 bat and 1 ball per customer. The owner of the store, Mr. Blake, thinks that a customer who purchases a bat is more likely to purchase a ball than a customer who does not have to purchase a bat. He analyzes sales from the last week and finds that a total of 240 customers came into the store. He counts 180 customers who purchased bats, 96 who purchased balls. Mr. Blake then counts the numbers of sales that include both a bat and a ball and finds 72 purchased both. Is there an association? So again, I would love it if you would pause this video and sort of see what you come up to, because I think you doing this is going to help a lot more than you watching me do it. So hopefully you've paused this and are coming back for the answer. So I don't know. We'll say, did you buy a bat? Yes or no? And did you buy a ball? Yes or no? He analyzed the sales first week, find 240 customers came into the store. 180 purchased bats, but it doesn't say anything about balls, so it must be a total. 96 balls, doesn't say anything about bats, so it must be a total. 72 bought both. So there we go. So this must be 60. This must be 24. This must be 108. This must be 36. This must be 144. Again, add them up this way. That seems to make sense. Add them up this way. That seems to make sense. So I think we're good. So is there an association between purchasing bats and balls? Well, let's just see. Did you buy a bat? How many people bought a bat? 180 out of 240. Which is 75%. All right. Then, given that you bought a ball, did you buy a bat? So we're only asking people that bought a ball, did you buy a bat? And it's 72 out of 96. So we'll divide 72 by 96. And we get 75% again. So we would say there is no association. It doesn't matter if you bought a ball, you're no more likely to buy a bat. By the way, if I had asked the opposite, if I had said, hey, what are the odds of did you buy a ball? And asked everybody, did you buy a ball? It's 96 out of 240. So we'll go ahead and say 96 divided by 240. We get 40%. And then I would have followed that up by saying, hey, given that you bought a bat, did you buy a ball? Right? So given that you bought a bat, did you buy a ball? And we would get 72 out of 180. And you would see that it doesn't matter which way you ask the question. Either way, our numbers don't change. It's either 40 to 40 or it's 75 to 75. Either way, the numbers don't change. We have no association. All right, so Shifty Shauna. Shifty Shauna, I didn't say that well, did I? Has a bad relationship with the truth. She doesn't usually tell it. In fact, whenever Shauna is asked a question, she rolls a dice. If it comes up 6, she tells the truth. Otherwise, she lies. So if Shauna flips a fair coin and you ask her which side has landed up, what is the probability she tells you heads and is telling the truth? Choose a method to solve this problem and carefully record your work. Be ready to share your solution with the class. So again, let's go ahead and pause this, see what we come up with, and then we will return to discuss it. I will set it up real quickly. Figure this out. So first of all, she got a die. She's a 6. There's a 1 in 6 chance of getting a 6. There's a 5 in 6 chance of not getting a 6. Again, this would be the truth, and this would be a lie, right? So if we figure this out, she'll tell the truth. So this she'll say head, and there's a 1 in 12 chance of this happening. Here she'll say tail, and there's a 1 in 12 chance of this happening. Here she would actually lie and say it was a tail, and there's a 5 in 12 chance of that happening. And here she would lie and say it's a head, and there's a 5 in 12 chance of that happening. So hopefully that all makes sense. Now, it says if Shauna flips a fair coin, and you ask her which side lands up, what's the probability she says heads and is telling the truth? Well, that's right here, right? Truth, head, there's a 1 in 12 chance. Suppose Shauna flips a fair coin and asks her if it came a heads or tails, what's the probability she says heads? Well, there's a 1 in 12 chance and a 5 in 12 chance, so altogether there's a 6 in 12 chance. So we'd say half the time she's going to say heads, but most of that time she'll be lying. Alright, suppose Shauna tells you that the coin has come up heads. What's the probability she really did flip heads? It would be 1 out of 6, right? There's 1 truthful way and 5 lying ways, 6 ways altogether. One of those 6 ways is the truth. And then it says, is whether Shauna lies or tells the truth independent of whether the coin lands on heads or tails. So first of all, let's just say, okay, what are the odds that you tell the truth? We know that there's a 1 in 6 chance of her telling the truth, which is 16.6%, right? Well, now we'll say, given heads, what's the odds that you tell the truth? So given heads, what's the odds that we tell the truth? And again, it's 1 in 6. which is 16.6%. So I would say there's no association. And remember, if there's no association, that means that they are indeed independent. It doesn't matter if what she flips her coin as heads or tails. What matters is what she spends on the dice. That's what matters. All right, so that wraps up that one. Last video is going to be a review.